Hey guys, Sebastian here with another Cardano video. This time we're going over the paper for Chimeric ledgers. So what is this for? So essentially in Cardano, we want to have the Cardano settlement layer, the SL, which uses the UTXO model similar to Bitcoin. But we also have the computation layer, which uses the accounting-based model similar to Ethereum. So the models in this paper are actually not quite Bitcoin, not quite Ethereum, and we'll see the differences later. But we'll quickly go over the paper, and describe the technique that they've used to try and unify these two systems to be able to facilitate cross-chain transactions and ledgers that can support both models. So a lot of this paper, at least at the beginning, is just describing what UTXO and accounting-based models are. So if you are all familiar with these terms, then it should not be a problem that we kind of skim over it. If you are not familiar with them, there are plenty of research online where you can find out more, and I'll briefly touch on it in this video. So we'll go over a few definitions really quick. So first we say a ledger is a list of transactions. Okay, and we define a few operators, right? So we define this : operator here, which means concatenation. We define this @ sign, which represents an address. We define the $sign over here to represent a monetary value. And then we represent a hash using this hashtag down here. Alright, so now we've gone over the basic definitions. We're ready to kind of go into the definition of UTXO that is used in this paper. Right, so what is UTXO transaction? Right, so it's a set of inputs and then a list of outputs, right? So this is a UTXO based transaction. So if you imagine in the UTXO, we take a bunch of, so an input in this case is a transaction and then an ID in that transaction, right? So you can imagine transaction 5, ID 2 will be like one UTXO, right? So it's a set of inputs, right? And then we also have our list of outputs. And the reason that it's a list of outputs is that because here our output is defined as an address and a coin, right? And then we need it to be an ordered list because later on when we use it as an input, we need to be able to use the ID of the transaction, right? So as we create an output, we'll say, okay, this is index 1, index 2, index 3, index 4. Then later on, if we want to reuse these UTXO that we just created in a later transaction, we can say as the input that the transaction number and the index number is well defined, right? So this is the brief definition of a UTXO transaction, but this is slightly different from Bitcoin in the sense that we also have this forge and fee, right? So what is forge and fee? Well, forge is essentially the idea of a coin-based transaction, right? So in Bitcoin, whenever you get paid for mining rewards, that'll come in a coin-based transaction. But here we're mixing it all into one system where instead every transaction has a forge parameter that defines how many coins are created out of thin air. And then we also have a fee value, which is just the transaction fee. So that's the definition of UTXO transactions that we're using. And so what are we trying to do with these? Okay, well essentially what we're trying to do first of all is figure out how you define a balance for an address in a kind of recursive fashion, right? So you say, okay, so what is the balance after a given transaction, right? So imagine we have a transaction that's kind of in the void. What is the balance for a given address given this transaction? Okay, and this is what we have over here. So you given an address, a UTXO transaction, and a ledger, we try and output the value. Okay, so this is the output of our function. Okay, so what we do, we sum over all the outputs where the output belongs to our address, right? And then we take out from this whatever we input, right? So we go over all of the inputs in a transaction where the inputs belong to our address and then subtract that. Right, so this is a fairly simple definition of a balance change given by a given transaction. And now that we have this simple function defined, then we can recursively go through a ledger, right? So we call ledger this lambda, and we say, okay, so if you have an empty ledger, then the balance of any address is just 0. If you don't have an empty ledger, then pop off a transaction from the top, right? So you can imagine a ledger is a list of transactions. So we're saying with this t colon colon, we're saying, okay, take the ledger and take the most recent transaction, pop it off ledger, calculate the balance for this given transaction, and then recursively go down and calculate the balance of the ledger without this transaction included, right? So you can see this lambda here represents the entire ledger without the t, or with t removed, and so we recursively go down and compute the balance. And this is our way of recursively defining a balance on our UTXO ledger. So now that we have this sorted out, by the way, we have examples, so you can kind of see how it works using the notation I outlined earlier. If you're interested, I'll have a link to the paper in the description of this video, so you can go through the examples yourself if you want. But now we have this. Now we're moving to account-based transactions, right? So this is similar to what we have in Ethereum. Right. The slight difference with what is in Ethereum is, again, we have this forged value that is part of the regular transaction system. So this is an accounting transaction. And so what is the difference between UTXO and accounting? Well, one of them, which is evident from this definition right here, is that any accounting-based transaction only has a single input and a single output, right? Which is different from the UTXO, which can have multiple inputs and outputs. Right, and so that's where we get this definition of option from, right? So if you're familiar with programming, you may know the concept of option or optional. If you do not know this concept, you can think of it as similar to the way you would use null or null pointer. Right, there's a slight difference, and if you want to know the difference, you can look it up. But essentially what we're saying is that sender is either an address or possibly nothing, right? And that's what this option represents, the possibility that there is no sender. And you might be wondering, why do we need to encode this possibility that there is no sender? Okay, and so this is essentially will be used later on when we try and define the how should I say, the transaction between UTXO and accounting. So if you want to send some UTXO transactions to accounting, you need to prove an equivalence between the two. That's what we're looking for, equivalence, right? So when we try and build the equivalence, we'll need this possibility of using null or none. And we use this essentially to say, okay, what if, for example, we have like a Coinbase transaction where we create money out of thin air? Well, we can say, well, if you just create money out of thin air, there is no sender, right? There's a receiver, but there is no address where this money came from. So the sender would be none, right, or null, or there is no sender, right? And similarly, we will also use a case where there is no receiver to encode the idea that we're paying a fee, right? We're just paying a fee into the void. Nobody's receiving the fee. We're just sending it out there, right? And that's kind of what this is about. We also have a nonce, which is similar to Ethereum. So we have a nonce to make sure that there can't be any double spend attacks. I shouldn't say double spend. This is like a replay attacks, right? Somebody could replay a transaction. If you don't know about replay attacks and how Ethereum blocks these kinds of attacks and how the nonce plays into it, you can look that up. Slightly different from the Ethereum model is that in Ethereum, the nonces have to be strictly increasing, right? In our paper, we put no such restriction. So theoretically, it'd be possible to have like 0, 10, 50, and non-increasing. You can have 50, then 10, then 0. It doesn't matter the order as long as they're all unique. All right, so this is a slightly looser model than what Ethereum proposes. So okay, so how do we define the balance on this? Well, the balance is much simpler. It's just if you've received money, your balance goes up. If you've spent money, your balance goes down, right? So it's again just received minus spent, which is similar to the definition we have for UTXO. In fact, if you look at the definition, I think this is actually a mistake. This should not be UTXO transaction. This should be account transaction. Whoever read the paper should probably fix this typo. But it's basically the same thing, right? Except you just swap the field. So then what's the definition for an entire ledger? Same thing as before. For an empty ledger, you just have 0. For a ledger of multiple transactions, you pop off the top transaction, you calculate the balance, for the specific transaction, and then you recursively calculate the balance for the rest of the ledger, right? And so you can tell the difference between these two cases, right, the UTXO versus the accounting-based model for calculating the balance, is simply this transaction type, right? But everything else stays the same. And so to a certain abstraction, these are similar models, right? Whoops. So now how do we define, how do we define the equivalence between these two systems, right? That's what we care about. Hold on. Yeah, so how do we define the equivalence between these two systems? Sorry, I like accidentally alt-tabbed earlier. Yeah, so first we want to go from accounting-based to UTXO-based. All right, so how do we do that? Okay, so if you imagine what we're trying to do is build two ledgers in parallel, in a sense, right? So we'll start with an empty ledger for the account-based model, and then we'll have another empty ledger for the UTXO model. And as we get a transaction on the accounting-based model, we will translate this to the UTXO model and build these two ledgers side by side. Okay, so if you were to try and do these, where you're building two ledgers side by side, how would you translate these transactions? Okay, so if you imagine you send money to somebody using account-based transaction, right? You just have a sender and then a receiver, right? This is different from the UTXO model, where in the UTXO model, you might remember there's a change address, right? So if you send like 5 bitcoins to somebody, but your UTXO contains 7 bitcoins, you'll send 5 to somebody, and then you'll receive 2 as change back to yourself, right? And so because of the system, you can imagine the UTXO system gets fragmented over time, right? First you have one address, then it gets split up, right? So you may have some money in multiple change addresses and all this kind of stuff. So everything gets split up into multiple addresses as you make transactions, right? Whereas the accounting-based model will simply keep everything into the same box, right? You only have one account. Okay, so this is essentially what we try and encode in this algorithm, right? So you say, okay, so in the UTXO model, you have a set of unspent outputs, right? So for lambda prime is our new ledger, so that'll be our UTXO. So in the UTXO model, you'll have a set of unspent outputs, right? So you may have one UTXO, two UTXO, whatever, and we pick a set of them such that the sum of the value inside this UTXO is larger than the amount you want to send to somebody, right? And so in this paper, we don't care how you pick the UTXO. You can pick the UTXO in various ways, right? In fact, IOHK has an entire document about how to select an input selection policy for UTXO that has different kinds of properties. But for the purposes of this paper, we say, okay, you have UTXO and you just need to pick a set of them. We don't care how you pick the set, you just pick a set of them such that you have enough money in this set of UTXOs to send the money to whoever you're sending money to, right? And so we pick our set of UTXO that is large enough to match the amount of money we're sending in the accounting-based transaction. Because remember, this is all based off an accounting-based transaction, right? And then in the UTXO ledger, we then create an input based off all these UTXO that we took. And then we have to create a new transaction also, which is an output, which is the change address back to ourselves. Right, so any accounting-based transaction will result kind of in a set of inputs, and then a new output back to our cells in the UTXO model. Right, so I hope this is fairly straightforward if you have a kind of an understanding of the way the UTXO model works. So this is kind of the simple case. So what does it look like when we're trying to go from UTXO back to the accounting-based model? And this case is slightly more complicated because, as I mentioned before, in the UTXO case, we actually can have multiple inputs and multiple outputs for any given transaction, right? Whereas the accounting-based case, we only have one input, one output. And so what this causes is that when we want to translate a transaction in the UTXO model, we actually need multiple transactions in the accounting-based model scenario, right? So the question is, how do we efficiently create these new transactions in the accounting-based model, right? And so the way we do this in this paper is kind of a heuristic, right? So let's kind of think about what you could do, right? So imagine you have some UTXO transaction that has, a set of inputs and a set of outputs, right? One thing you could do is to model this in the accounting-based transaction, you could send an amount of money here in one transaction, then send another amount of money here in another transaction. And then in this case, you make another transaction and another transaction. And here in this third account, you make another transaction, right? So if you have this scenario, then the number of transactions you have to do in the accounting-based model is, m times n, right? Where m is the number of inputs and n is the number of outputs. Maybe I switched m and m compared to what is in the paper, but like the idea is the same, right? You'll end up having a large number of transactions, which is number of inputs times number of outputs, right? So we want to try and avoid that. So let's think again about the minimum number of transactions you can have in this kind of scenario. Well, if you have, for example, the same number of inputs as you have outputs, and they're all exactly the same balance, right? So maybe you have like a 5 ETH in the top one, so you'd have like 5 here, and maybe this also expects 5. It wouldn't be exactly 5 because you'd have to count for the fee, but suppose, right? And then, similarly, this would be 3 and this would be 3. So imagine they're all exactly the same. Then you can do a simple transaction here, and then a simple transaction here, and a simple transaction here. Right, so in the best case, the number of transactions that we need is actually the max of the two. So I think it's actually written somewhere. Yeah, you would only need the maximum of either n or m, right? So this is our best case. All right, so what can we do with an algorithm to try and build a heuristic to get as close to this best case as possible, whereas we still are able to calculate the answer fairly fast? And so in this paper, we outline an algorithm that it runs in n plus m running time. Okay, so it's kind of in between the two, and this is the worst case, right? And in best case, we will actually achieve this max n m scenario. All right, so what do we do? How do we do this? Okay, so what we do is we first build two queues, right? So we have one queue which is our senders, and another queue which is our receivers, right? And so these are what SS and RS are. So this is SS for senders, and then we have RS for receivers, right? And so you can imagine in this case, you put, your 5 here, and then you put your 3 here, and you put all this senders, and then you also in the receiver queue, you put in all your receivers, okay? And obviously these don't have to be the same number. You could have more receivers and senders and whatever. And we want to write an algorithm that in every iteration of a loop, we get rid of at least one of these, right? So maybe we get rid of one sender, maybe we get rid of one receiver, but we just get rid of at least one, okay? And because of this, if we have such an algorithm, then the number of iterations of this loop is just n plus m, right? Because every iteration will take care of one element, and you only have, n plus m elements total, right? And we also want, in the best case, that we remove 2 elements for every iteration, right? So this would be the best case because then we will only have the max of M and M transactions. Okay, so how do we do this? This is the idea, and so the actual implementation is you say, okay, so what is the expected number of transactions? Okay, so expected number of transactions, we assume we will hit the best case. So you say, okay, the expected number of transactions is our best case scenario, where we have max of number of senders and max of the number of senders and number of receivers. Okay, and so for our UTXO transaction, we will have a given fee and a given forge represents our Coinbase. And we say, okay, we'll split this up equally amongst every transaction, right? So it's kind of hand wavy in the sense that, like, if you translate to another ledger, maybe if you split the fee, it might be too low and it wouldn't really work. But for the purpose of this paper, we kind of just hand wave and say, okay, imagine we can just split up the fee, and the fee is always an acceptable number, and all the transactions will go through in the ledger, right? So okay, so for every node, remember we have these two columns which represent our input and output, or sorry, senders and receivers. We say, okay, so for every sender, we have a value called rem spend, which denotes how much money we have left to withdraw from this account. So imagine, this has 5 ETH, and we send 3 ETH over here, then rem spend would be down to 2. We'd have 2 left in this account, right? And similarly, rem receive represents how much is left to be sent to a given receiver, right? So if this guy expects 3 and we only send 2, then the rem receive would be down to 1. Okay, so what we do is we say, okay, create a new variable called v and set it to rem spend minus fee plus forge, right? Because remember, we have to pay the transaction fee out of the sender side, and then because of our way the model works, any transaction in our model could potentially include money created out of thin air out of what would otherwise be known as a Coinbase transaction. Okay, and now we check, as I mentioned earlier, is the number equal to rem received. So this would be as if, like, we had 5 here, and then more or less 5 here, like give or take the fee and forge, right? So if they're equal, then we essentially pop off from our queue. Remember, we had these two queues. We essentially pop off the bottom 2 elements, right? We say, okay, we've satisfied both of them, and we're good to go. Okay, so what if they're not equal, right? What if this guy expects, for example, let me erase this real quick. What if this guy has 4 ETH and this guy only needs 2, right? So what we say is that we need to change the fees, okay, whenever this happens. And how do we change the fees? Well, we say take the old fee and multiply it by v over rem received, okay? So actually, it'd be better in this case if I did 2 and 4, I think. Let's see. Okay, actually, yeah. So we can do 4 and 2. So basically, what happens is we have 2 cases. One is v is smaller than rem received, and the other one is v is larger than rem received. Okay, so essentially what we're saying is that if we, in this case, the specific case I'm drawing here, whenever we sent 2 ETH, then we're left over with 2 remaining, right? So our ratio would be 4 over 2, right? Which is just equal to 0.5, right? So we have a ratio of 2 to 1, and this represents how much we have overflowed, not overflowed, but how much we have in abundance in this spender. Okay, and then we essentially modify both the fee and the forge to match, right? So we say, okay, if we have more than the number that we need to send. Then we say, okay, we take the fee and we multiply it by, in this case, this would be 2. My bad. I went the other way around. This would be 2. And in this case down here where it's larger, then we would do 2 over 4, which would indeed be 0.5 as I mentioned earlier. Okay, so we say, okay, so because we have twice as much, we will multiply our fee by 0.5. Okay, so essentially we will put half the fee in this transaction, and we will keep this item in the stack, right? So only pop off the received and keep the sender, and when we reuse the sender, then the fee remaining will only be half, right? So essentially we take the whole fee, split in half in one transaction and half in the other transaction. Okay, so now that we defined how to pop items off our stack and send to transactions and how we deal with the fees, multiplying the fees by some ratio such that the fees end up working out, we now have a loop that runs in worst case n plus m time. There's a slight trick or corner case you have to deal with, which is to say, what if you run out of senders, but you still have some amount that is receivable? And to deal with that, you say, okay, so if we're out of senders, but we still have some account receivable, that means that all that is left must be forge money that comes from the forge, money that comes from the equivalence of what would otherwise be a Coinbase transaction. Similarly, if we run out of receivers, but we still have some money that we're supposed to send, then that means that we must be in a case where all the money that is remaining is meant to be paid in fees, which is why we create a transaction down here that has a sender but no receivers, and essentially just pays a fee. And so these are two last cases, and hopefully with this you're convinced that every iteration of our loop will get rid of at least one receiver, one sender, or in best case both. So now that we've defined the translation between UTXO to accounting and also accounting to UTXO, now we have to think about how we would mix these together. So there's one caveat I haven't mentioned, and that is to say, when you're translating from UTXO to accounting, I mentioned that we would need to create multiple transactions, right? And this is problematic because what if you make multiple transactions and one of them fails but one of them goes through, or maybe one of them goes through and the other one gets stuck in queue in the mempool and goes through like a day later, a few hours later. It doesn't really work that well, right? So we need some sort of atomicity to transactions. That is to say, either it all goes through or they all fail and they're all done at the same time. Right, this is kind of the property we want. Okay, so to do this, we define a hybrid transaction, and we define it from a very broad perspective, where an input is just a map of addresses to values, and the output is also just a map of addresses to values. And this lets us represent both systems in a single transaction, as long as we still keep the nonce and the forge and the fee for all transactions, right? So now that we have this very high level hybrid transaction, we define these two functions that let us essentially go from one layer to the other, right? So imagine we're in the UTXO layer, we want to go to the accounting, or the other way around. And the way this is set up is to kind of imagine ATM, okay? So imagine you have, a bunch of paper bills. Some are 20, some are 10, whatever. You have a bunch of paper bills. This is the image for the UTXO transaction, right? You have a bunch of different items, each worth a some amount of money. And then you go to an ATM and you deposit to the ATM, and then that all gets merged into one bank account, right? And so this is what they mean by the deposit transaction, right? We have a set of inputs, which is from our UTXO, and then we have one address that we're depositing everything into, along with the forwarding fee, as always, right? The withdrawal transaction is kind of the opposite, right? So that's to say, imagine you have a ATM and you have some amount of money in it and you want to withdraw, right? You will get back a bunch of paper bills, and so this is the image where we have a withdrawing address, and then the output can be a list of outputs. So there's a few different things with this. So this is what's laid out on the paper. You can think of a few ways that maybe you might want to improve it or change this, right? One thing is, for example, whenever you deposit money into the ATM in their example, you have to deposit your entire UTXO value, right? Because notice there is no change, right? So imagine you have one UTXO that's worth, 5 Bitcoin, and you only want to transfer 3 Bitcoin to the computation layer. With this system, you wouldn't be able to do it. You have two options. Either you could deposit all 5 and then withdraw back 2, or the other option is you could take your 5, split it up into a 3 and a 2, right? Make a transaction to yourself to split it up into a 3 and a 2, and then now that you have 2 UTXO, you would essentially send the 3 into the ATM and keep the 2 in the UTXO model. So basically this means that no matter which way you would do it, you would need an extra transaction to send the exact number you want, right? Which may not be desirable, although this model currently is more simple. Similarly, in the withdraw case, the model supports a list of outputs, right? So you could theoretically withdraw a bunch of UTXOs, but in practice, maybe people don't really care and they would rather, for performance reasons and simplicity, receive all their UTXO in just one transaction. So you wouldn't need a list of outputs, you could just have one large UTXO. So that's another possibility. There's a forum thread on this topic, actually. So if you go on the forums in the education section, there's a section on the paper on chimeric ledgers, and one of the members here made a proposal, which I also thought was interesting, where they say instead of the model proposed in the paper, we would essentially have a universal transaction, right, which is defined similar to the UTXO case, except we redefine what is an input and output. So in this case, input is now either UTXO input or account input, and then output is either UTXO output or an account output, right? And so the benefit of this system is now we can have a single layer that supports transactions of both types, right? So in the example he gives here is now you could have a transaction that's for input 1 UTXO, and for input output there's a bunch of UTXO along with one account. And similarly, you could also have UTXO and account as an input, and another UTXO, another account as an output, right? So this is kind of a different way you would go about it. It doesn't really work that well with the concept of Cardano, in the sense that in Cardano you have your settlement layer which only accepts UTXO, and the competition layer which only accepts account-based. So in this system where we have two chains in general, each only accepting a certain model, you wouldn't be able to have what is outlined in this forum post where you could combine the two. You'd have to create a new chain for that. But I thought it was an interesting idea. And so that's it for the Chimeric Ledgers paper. There's some discussion in the end. If you want to read the paper in more detail, there's a link to the paper in the description. Hopefully you found this useful. If you want more videos, you can always follow me on YouTube, find me on Twitter, all this kind of good stuff. And I look forward to making more content for you guys soon.